In this video, we're going to try to prove the following result. The absolute value of the integral of the product of g of x and f of x between a and b is less than the square root of the integral of f squared times the square root of the integral of the g squared between a and b. So this theorem or this result gonna give us a upper bound and a lower bound of the product of two functions. In our case, we assume that f and g are continuous on AB, a certain interval AB, where a and b are real numbers. Before proving this result, we can state some facts. If we have a function that's positive, its integral is positive as well. Also, if we have a polynomial of degree 2 and it's positive, its discriminant delta is going to be less or equal than 0. Okay? These two facts we're going to use here to establish this result. Let's define a polynomial p of lambda as the integral between a and b of f of x minus lambda g of x squared. Okay? In this case here, we have we see that we have this is a positive value because it's squared, and therefore this value is greater or equal than 0. Okay, because using this fact here, so think of this f of x minus lambda g of x as being our f, and it's bigger than 0 because it's squared, and therefore the integral is bigger than 0. Okay, now we can expand. We can expand this square here inside, and using the linearity of the integral, and using this fact here, we can prove this result. You can stop here and use these facts or this result, and you can prove this statement here. Okay, let's solve it then. So we have p of lambda. We can expand and we get f squared dx minus 2 lambda f of x g of x plus lambda squared g squared and t of x. And using the linearity of the integral, we can write this as the integral between a and b of f squared dx minus, I'll take 2 lambda outside because it's just constant, and I have f of x, g of x, d of x plus lambda squared, the integral between a and b, g of x, d of x. I did nothing new. I just expanded this one here, and I used the fact that the integral of lambda x is lambda the integral of f here. Now this is one more fact. These are numbers. The integral between a and b of f of x dx is in R. It's just a number. Okay? Therefore, we have this is a number, this is a number, this is a number, and therefore this is a polynomial that depends on lambda. Let's compute delta, the discriminant. We're going to call it delta p. So the discriminant of this polynomial. So here we can think of this one as this is our a, and this is our b here with the 2, and this is our c. Okay, we have delta is b squared minus 4ac. B squared in this case is minus 2 times this one is going to be 4. The integral between a and b of f of x, g of x, dx minus 4 a times c. A is this one here. The integral between a and b of g squared dx times f, which is the integral between a and b f squared dx. And note that this one, since this one is positive, is going to be less than 0 because this is our delta. If this one is less than 0, we're going to have in, I forgot here to put this one square because this is b. I should square this one. b is this one minus 2 lambda, the integral between a and b of f of x, g of x. So this is squared. And if it's less than 0, therefore this means that the integral between a and b of f of x, g of x, d of x squared is less than the integral between a and b of f squared dx times the integral between a and b of g squared dx. Okay? Now, taking the square root of everything, we're going to have the absolute value of the integral between a and b f of x, g of x, d of x less than the square root of this one. It's going to be the integral between a and b of f squared dx times the square root of the integral between a and b of g squared dx. And therefore, this is what we needed to prove. Okay? This is the result that we are looking for. And we have done it. And this result gives us a relationship between two functions, f of x and g of x. All we assume is that both f and g are continuous on this interval a, b. Okay? And we're going to use this result to prove many others. Okay? For those of you who are advanced, this is a great result to learn, and you need to have it in your tools. Okay? And next we're going to do one more or an application of this one. But the key idea here is that this result here is between f and g, and it's giving us an upper bound of the product. We assumed many things here, and we used many results. If f is positive, the integral of f is going to be positive. If we integrate a lambda times a function, it's going to be the lambda outside. We take it outside, and it's going to be times the integral. The integration is linear. And also we use this fact here that the integral of any function between a and b constants is a constant. It belongs to R, the set of real numbers. And the key here is to use that when you have something, a polynomial of second degree that's positive, its discriminant is going to be negative. And that's what we use here. Okay? And if you have any questions, if you like the video, share it. If you don't like it, please feel free to hate it or dislike it. Okay? Comment and subscribe. And we're going to add more videos. Thank you very much.